Hipparchus of Nicaea was a Greek astronomer, geographer, and mathematician. He is considered the founder of trigonometry but is most famous for his incidental discovery of precession of the equinoxes. Hipparchus was born in Nicaea, Bithynia, and probably died on the island of Rhodes. He is known to have been a working astronomer at least from 162 to 127 BC. Hipparchus is considered the greatest ancient astronomical observer and, by some, the greatest overall astronomer of antiquity. He was the first whose quantitative and accurate models for the motion of the sun and moon survive. For this he certainly made use of the observations and perhaps the mathematical techniques accumulated over centuries by the Babylonians and other people from Mesopotamia. He developed trigonometry and constructed trigonometric tables, and he solved several problems of spherical trigonometry. With his solar and lunar theories and his trigonometry, he may have been the first to develop a reliable method to predict solar eclipses. His other reputed achievements include the discovery and measurement of Earth's precession, the compilation of the first comprehensive star catalogue of the Western world, and possibly the invention of the astrolabe, also of the armillary sphere, which he used during the creation of much of the star catalogue. It would be 3 centuries before Claudius Ptolemaeus' synthesis of astronomy would supersede the work of Hipparchus. Life and work. Relatively little of Hipparchus's direct work survives into modern times. Although he wrote at least 14 books, only his commentary on the popular astronomical poem by Aratus was preserved by later copyists. Most of what is known about Hipparchus comes from Strabo's geography and Pliny's natural history in the 1st century, Ptolemy's 2nd century Almagest, and additional references to him in the 4th century by Pappus of Alexandria and Theon of Alexandria in their commentaries on the Almagest. There is a strong tradition that Hipparchus was born in Nicaea, in the ancient district of Bithynia, in what today is the country Turkey. The exact dates of his life are not known, but Ptolemy attributes to him astronomical observations in the period from 147–127 BC, and some of these are stated as made in Rhodes. Earlier observations since 162 BC might also have been made by him. His birth date was calculated by Delambre based on clues in his work. Hipparchus must have lived some time after 127 BC because he analyzed and published his observations from that year. Hipparchus obtained information from Alexandria as well as Babylon, but it is not known when or if he visited these places. He is believed to have died on the island of Rhodes, where he seems to have spent most of his later life. It is not known what Hipparchus's economic means were nor how he supported his scientific activities. His appearance is likewise unknown. There are no contemporary portraits. In the 2nd and 3rd centuries coins were made in his honor in Bithynia that bear his name and show him with a globe. This supports the tradition that he was born there. Hipparchus is thought to be the first to calculate a heliocentric system, but he abandoned his work because the calculations showed the orbits were not perfectly circular as believed to be mandatory by the science of the time. As an astronomer of antiquity, his influence, supported by ideas from Aristotle, held sway for nearly 2,000 years, until the heliocentric model of Copernicus. Hipparchus's only preserved work is tau nu rho alpha tau omicron upsilon kappa alpha epsilon delta omicron xi omicron upsilon phi alpha iota nu omicron mu epsilon nu omega nu xi eta gamma eta sigma iota sigma. This is a highly critical commentary in the form of 2 books on a popular poem by Aratus based on the work by Eudoxus. Hipparchus also made a list of his major works, which apparently mentioned about 14 books, but which is only known from references by later authors. His famous star catalogue was incorporated into the one by Ptolemy, and may be almost perfectly reconstructed by subtraction of 2 2/3 degrees from the longitudes of Ptolemy's stars. The first trigonometric table was apparently compiled by Hipparchus, who is now consequently known as the father of trigonometry. Modern speculation. Hipparchus was in the international news in 2005, when it was again proposed that the data on the celestial globe of Hipparchus or in his star catalogue may have been preserved in the only surviving large ancient celestial globe which depicts the constellations with moderate accuracy, the globe carried by the Farnese Atlas. There are a variety of missteps in the more ambitious 2005 paper, thus no specialists in the area accept its widely publicized speculation. Lucia Russo has said that Plutarch, in his work on the face of the moon, was reporting some physical theories that we consider to be Newtonian and that these may have come originally from Hipparchus. He goes on to say that Newton may have been influenced by them. According to one book review, both of these claims have been rejected by other scholars. A line in Plutarch's Table Talk states that Hipparchus counted 103,049 compound propositions that can be formed from 10 simple propositions. 103,049 is the 10th Schroeder-Hipparchus number, and this line has led to speculation that Hipparchus knew about enumerative combinatorics, a field of mathematics that developed independently in modern mathematics, geometry, trigonometry, and other mathematical techniques. Hipparchus was recognized as the first mathematician known to have possessed a trigonometric table, which he needed when computing the eccentricity of the orbits of the Moon and Sun. He tabulated values for the chord function, which gives the length of the chord for each angle. He did this for a circle with a circumference of 21,600 and a radius of 3,438 units. This circle has a unit length of 1 dark minute along its perimeter. He tabulated the chords for angles with increments of 7.5 degrees. In modern terms, the chord of an angle equals the radius times twice the sine of half of the angle, i.e., chord equals r. He described the chord table in a work, now lost, called Tun and Kukloyutheon by Theon of Alexandria in his 4th century commentary on the Almagest I-10. Some claim his table may have survived in astronomical treatises in India. For instance, the Surya Siddhanta. Trigonometry was a significant innovation, because it allowed Greek astronomers to solve any triangle, and made it possible to make quantitative astronomical models and predictions using their preferred geometric techniques. For his chord table, Hipparchus must have used a better approximation for pi than the one from Archimedes of between 3 + 1/7 and 3 + 10/71. Perhaps he had the one later used by Ptolemy, 3/830, but it is not known if he computed an improved value himself. But some scholars do not believe Aryabhata's sin table has anything to do with Hipparchus's chord table, which does not exist today. Some scholars do not agree with this hypothesis that Hipparchus constructed a chord table. Bo. C. Klintberg states, with mathematical reconstructions and philosophical arguments I show that Toomer's 1973 paper never contained any conclusive evidence for his claims that Hipparchus had a 3,438 base chord table, and that the Indians used that table to compute their sign tables. Recalculating Toomer's reconstructions with a 3,600 radius, i.e., the radius of the chord table in Ptolemy's Almagest, expressed in minutes instead of degrees, generates Hipparchian-like ratios similar to those produced by a 3,438 radius. It is therefore possible that the radius of Hipparchus's chord table was 3,600, and that the Indians independently constructed their 3,438-based sign table. Hipparchus could construct his chord table using the Pythagorean theorem and a theorem known to Archimedes. He also might have developed and used the theorem in plane geometry called Ptolemy's theorem, because it was proved by Ptolemy in his Almagest. Hipparchus was the first to show that the stereographic projection is conformal, and that it transforms circles on the sphere that do not pass through the center of projection to circles on the plane. This was the basis for the astrolabe. Besides geometry, Hipparchus also used arithmetic techniques developed by the Chaldeans. He was one of the first Greek mathematicians to do this, and in this way expanded the techniques available to astronomers and geographers. There are several indications that Hipparchus knew spherical trigonometry, but the first surviving text of it is that of Menelaus of Alexandria in the 1st century, who on that basis is now commonly credited with its discovery. Ptolemy later used spherical trigonometry to compute things like the rising and setting points of the ecliptic, or to take account of the lunar parallax. Hipparchus may have used a globe for these tasks, reading values off coordinate grids drawn on it. Or he may have made approximations from planar geometry, or perhaps used arithmetical approximations developed by the Chaldeans. He might have used spherical trigonometry. Aubrey Diller has shown that the Klima calculations which Strabo preserved from Hipparchus were performed by spherical trigonometry, with the sole, accurate obliquity known to have been used by ancient astronomers. 23 degrees 40. All 13 Klima figures agree with Diller's proposal. Further confirming his contention is the finding that the big errors in Hipparchus's longitude of Regulus and both longitudes of Spica agree to a few minutes in all three instances, with a theory that he took the wrong sign for his correction for parallax when using eclipses for determining stars' positions.